Welcome to CS42 on Monday, July 28th, 2014.
And anyways, I guess if you turn it in early, you can still credit. You get extra credit. But unlike kernel 1 and 2, if you want to turn in too late, there's no way to get it to be turned in the next deadline because there's no more next deadline. This is the last deadline. So you can still have 1 day late, but not beyond that. Okay. And again, if you have code from previous semester, please make sure not to copy from it. And the grading guideline is the only way we grade, and make sure you verify your submission. And as before, kernel 3, every branch of your code must have at least one DBG statement. And somebody is pointing out that there are functions that maybe there's no way to reach it. You can just leave it as not yet implemented, or just put a k-assert there, so that if the code executes there, you will get a, you will get a kernel panic, and that's perfectly okay. All right. All right, there's one change in the kernel 3 grading guidelines for fork bomb. I guess before the weekend, it says run fork bomb for 2 minutes, but that was like, in 2012 when the machine was slower. These days the machine gets really fast. So I don't want to get into the case where people actually they have such a fast machine that they will run out of memory. So I'm changing that from 2 minutes to 1 minute. So if you can survive fork bomb for 1 minute, then that will be good. Also, if the grade is C, I'm fork number 2,000. So if you fork 2,000 times, that's also qualified for a successful test in the fork bomb. Okay. And also, somebody was pointing out that for fork bomb, you can switch to a different TTY. In QEMU, you just type F2 or F3. The idea for fork bomb is that I guess my understanding is that if you run fork bomb, you still have the prompt, so you can still type in commands. So you should be able to continue to type hello, and even I guess after you run it for 1 minute, you can type /sbin/halt, and it will halt the processor. Okay, so please don't switch. So if your code has to switch to a different console in order for you to type commands, then you're not doing it right. Okay, something is wrong. You need to get it fixed. I hope you're having fun with kernel 3. If you're not having fun, at least I hope you're learning a lot. Because it's pretty interesting stuff. And the Unix code, the Unix kernel is written by people who are really good at operating system, and it's a really nice, clean piece of code. And I hope that by reading a lot of their code, you can learn from them. The final exam is next Monday during class, so it will be 110 minutes. It will cover everything up to the end of this Wednesday's lecture. I guess there's a typo right here. Lecture. Oh, sorry, there's a space right here. Minus the midterm coverage, right? Everything covered in the midterm will not be, in the coverage of the final exam, and plus kernel 2 and 3. And again, the exam is going to focus on operating system in general. So unless the question says Unix, you must not assume that the question is about Unix. Okay, so most of the questions are about operating system in general. All right. So today, we have a lot to cover because we still have two major topics to cover. We need to finish the devices. Hopefully, that will take 10 minutes, 15 minutes, and then we need to cover virtual machine and scheduling. Okay. So my plan is to cover virtual machine today and cover scheduling on Wednesday. I'm hoping that I can keep my schedule. All right. So last time we were talking about these devices, and we talked about that there are the other ways to handle the terminal. One of the points is that there are applications who doesn't want the line discipline module. For example, if you are running a game, on Windows or something like that, then you don't really want character composition. You don't want you want the up arrow to do something and not wait for character return before you process the input. Okay, so in that case, you want to completely bypass the line discipline module. Okay, so that's one reason to skip it. And also, I sort of mentioned that line discipline module, there are different ways to implement it for different locale. So again, modularity becomes important. Modern systems don't even have terminals, and they have bitmap display like you have in Ubuntu, Ubuntu, and also in Windows, in Mac. So in that case, you have a bitmap graphic display, and the window manager is the one that controls, and it's the window manager that's actually dealing with the keyboard and the mouse, and also doing the display. So when you try to display something, the window manager will send the character you try to display to the correct application. Okay, so in that case, we don't really have terminal. We have something called pseudo terminals. Okay, pseudo terminal. So even like when you secure shell to nunkey, you're not really connected to a terminal, right? But you are, as you sort of feel like you're on a terminal on nunkey. So again, that's not the real terminal. There's no real terminal device. So the scenario is very similar, that you're talking to a pseudo terminal. Okay. So for when you have windowing environment, then the one that's actually reading from the keyboard is called window manager. Okay. The window manager, they use queues to talk to the keyboard and the mouse. So every time you type in a key, every time you move a mouse, you generate an interrupt. The interrupt, send data to this queue, and then the window manager can pick it up, and they will send it to the one that are running in the window in the display system, where you have different applications. Depends on which one is the active or the keyboard focus. That's the one that's going to get your keyboard key presses. Okay. And when your application is running, when they decide to send data to the display, again, they will talk to the window manager, and the window manager will put the characters, into the display. Okay, and the window manager, when you use the mouse to click around, it knows which is the application that you want to receive the keyboard focus. Okay, what's more important is that window manager doesn't really run in the kernel space; it actually runs in the user space. Okay, so the real picture looks more like this, where you have the window manager running over here. It's taking data in, from the keyboard device driver, and this queue that I saw before, sits inside the kernel. So it's very similar like the picture that we saw before. Okay, except that the window manager basically talks to the pseudo terminal, and the way the pseudo terminal is implemented, it's actually divided into two parts. So the window manager, when it interacts with this particular device, it will look like it's talking to a device, okay? But turns out it's another module inside the kernel. So the window manager, if they receive a character and try to send it to the application, it will just send it to the pseudo terminal master over here, and it gets shipped to the pseudo terminal slave. And now the application can pick up the data as if the pseudo terminal slave is the device driver. Okay, so when you have an architecture like this, you can actually even do something even more crazy, is that I can actually have these two things run on different machines, where over here I have one machine running. For example, this could be nunkey, okay, and this could be your laptop, where your laptop is actually receiving the characters, and then things can get received over on the nunkey machine. Okay, so this way, okay, where is that picture? Okay. Anyways, so the data flow is going to be, I guess, let's see. Okay, so the data flow is going to be when you get the keyboard keys, the data travel this way. Okay, and you can sort of decide whether you want to bypass the line discipline module or not. If you don't want the line discipline module, then it's becoming more like this. Okay, so this way you can interact directly with the window manager through the pseudo terminal devices and then get the raw characters and the mouse movement directly from the window manager. All right? Okay, so that's, that sort of summarize, what we're doing with the terminal devices. And mostly these days, we deal with pseudo terminal devices. The other device that we're going to talk about briefly is network communication. Okay, so this is like talking to the internet. You have a network communication card, network interface card. That's going to be the device, and it comes with a device driver. So as it turns out that, the operating system interface for talking to networking devices and a terminal, well, it's the same interface, right? You open, you read, and you write because devices are treated as files. Okay. But network interface, so from the programmer's perspective, they're pretty much the same, okay? But inside the operating system, they need to be treated differently, okay? And there are two major reasons the network interface and the terminal needs to be treated differently. Number one is that the performance is crucial in network communication, okay? The networking speed comes at a really high speed. You have gigabit Ethernet. Data can come in at a very, very high rate. When you're dealing with a terminal, the user can only read so fast, so displaying on the terminal doesn't have to be so fast. And typing, you can easily deal with interrupts and read character one at a time from the keyboard device. Okay, and networking, the data comes at a much faster rate. Okay, so one is that performance is very crucial in network communication. Okay, and the other reason is that networking is actually fairly complicated. Okay, the terminal is it's a relatively simple device. The networking, in order for networking to work, the networking are usually done in the programming in networking is done in a layered fashion. Okay, so we sort of have to worry about passing data from one layer to another. Okay, I don't know if you have taken a networking class. You probably read about the 7 layer of the internet protocol. So the data traveling at the lower layer need to be passed down to one layer higher, and then get passed to another layer, go all the way to 7 layer, all the way to the application. Okay, so if you have to copy data from one layer to another, and there's a lot of data that comes in, for example, if you download a web page from the internet, the web page might be hundreds of kilobytes long, maybe even megabytes long. Okay, you download a PDF file. Okay, so again, that data is a lot of data, and if you want to pass the data from one layer to another layer, how do you pass data from one layer to another layer? Okay, if you want to worry about modularity and you want the layer to be sort of loosely coupled, then usually you end up copying data. Okay, but if you have to copy data megabytes at a time, well, that's going to take a lot of time. Okay, so therefore, in networking, you cannot afford to copy network data from one level to another. Okay, you have one data sitting in a queue. If you want to move it to another queue, well, you're only allowed to copy pointers and really not data. Okay, so therefore, you should really not copy anything at all, especially not data. You're allowed to copy, data structures. So therefore, in order to support that, you need kind of special data structures. Okay, so you can only pass, using again one level of indirection. All right, so that's the main difference. Here's a picture that talks about this layered communication where you have TCP/IP. So TCP/IP is 2 of the networking layer, inside the multiple layer networking architecture for the internet. So the idea over here is that when you send data from the higher layer to the lower layer, what you do is that the part of the data is that you send, you also attach a header to it. Okay, the header tells the the receiver what to do with that particular piece of data. Okay, so as you send data, so for example, if your application is file transfer protocol (FTP), okay, this data when you try to send it to another machine, what happens is that the FTP data is sitting right here. As it goes through the TCP layer will add a TCP header to it, and then it gets passed down to the lower layer. The lower layer, the next layer is IP. IP will treat this entire thing from TCP as data, because IP is really not allowed to peek into what data that's passed down from the previous layer. Okay, so as far as IP is concerned, this is the data. Okay, and then it will add a header to it, and then send it down to even a lower layer. Okay, so every time as the data travel to a lower layer, the data get bigger and bigger and bigger, and they get traveled to the other side of the network, and the other side of the network does the reverse operation by stripping off data, by stripping off the header, and then pass the data up a protocol layer. Okay, so the trick over here in the networking, sort of networking subsystem is that you have to make sure that you don't really copy any data, that you're allowed to pass these data around without copying anything, because copying things are too slow. Okay, so over here, that's what it's saying. Okay, you should need to do it without copying data. The way it's done, sort of in Linux, is to use something called the socket buffer. Okay, so socket is just like it's an internet connection. When you try to connect to the internet, it's like connect to a power source. So the idea here, you plug into a socket, and then you have connection. Okay, so that's just a name, that people use. And in the operating system, the socket is represented as a file descriptor, right? Because everything is treated as a file. So a socket, if you look at the socket is just an integer, and they represent an open file descriptor. Okay, so you can use the socket to read and write in order for you to do communication. Okay, so that's why they use the word socket. And the socket buffer is the trick that you have to use in order to make sure that you don't copy any data. Okay, and it sort of looks like this. Okay, so here's the socket buffer. It's a bunch of pointers, not very surprising, right? Anytime we want to have level in direction, we just have an array of pointers. So this is the data structure of pointers. This is the actual buffer, okay? And we want to make sure that when we pass this buffer around, we never copy any of the data, okay? So therefore, in this particular picture, we have, this is where the data buffer is, and the data are coming from the other side of the internet, and, the data, we're going to sort of parse the data inside this buffer to determine which part is the header and which part is the data, okay? And maybe there's some description of what's actually in here in that data structure, okay? And then we use the socket buffer to point to a different section of this buffer, okay, while allow the buffer to continue to be filled. Okay, so what happens in the Internet Protocol is that if you want to transmit a 1 megabyte file, which is pretty big, you tend to transmit it, a few kilobytes at a time. Okay, so what happens is that on the other side, when you receive the data, you're going to construct the message piece by piece. Okay, so over here, the data might be coming over the internet all over the place over here. They might come in different order. Okay, and then eventually when you get to your machine, you have to assemble, put all the packets together to form a message. And when you finish forming the message, you should pass the message to the higher layer. Okay, so over here, this picture sort of shows you that you allocate this particular buffer so that more stuff can actually go into the buffer as packet arrive across the internet. Okay, so this one shows you that, here's one message for you, and here's another message for you, and they're kept track of inside the internet. Okay, so how does this guy help? Okay, if you look at the pointer over here, this guy points to where the header is, and this guy points to where the data is. Okay, so inside the networking subsystem, you're deciding to parse the data already and try to figure out which part is the header and which part is the data. Okay, and later on you will pass only the data to the higher layer. Okay, and then over here it tells you where the tail is, so that in this case, if you want to fill in more data, you'll fill in at the end. Okay, and also here tell you where the end of the data is, and that's the limit of the of this particular buffer. Okay, and then you use linked list to point to other segments, other communication with a different machine, maybe. All right. So in that case, what you can do is that when you need to pass to another module, okay, from one side of the kernel to pass to another side of the kernel. This is not about passing, up the protocol level, but just pass to another module. You say, hey, here's some data. Maybe at delay processing, deferred processing, you need to pass data from one side to another. Well, now you don't have to copy the buffer. All you have to do is to copy the socket buffer. Okay, so here's data that's being shared by two modules. One is using this data structure, and when you need to pass it to another module, all you have to do is to copy the entire socket buffer by using a mem copy. And all of a sudden, this guy all points to the same place, and this thing can also work on it. All right? If you want to pass it to the next level module, what you need to do is that you need to take the data and parse the data into header and data, right? Because that's the next higher level module. So what you do is that you start with something like that, and then the higher side can actually change the head pointer, because now this is the higher level. The higher level will take this data and divide the data into header and data for that particular level. Okay, so therefore this guy can adjust the header so that the header will move right here and data will again move right here. And now this guy will think that the data is going to be looking like this. Okay, but that's at a higher level, so the amount of data becomes smaller. Okay, so again, you can pass data from one level of the TCP/IP protocol layer to the higher layer without copying any data. Okay, so this keeps going up all the way to the application layer. All right, so this way, you only copy these data structure, and that's how you achieve, the small amount of copy. All right, I just added an X to this slide, to save time in today's lecture. Okay, so anyway, so that's all I want to talk about as far as, networking is concerned. Okay, so let's continue to section 4.2, of chapter 4. And this one is titled about rethinking the operating system structure. Okay? So this is kind of like, the future in the good old days. When we talk about, what is the old operating system architecture? Well, the old operating system is the monolithic operating system. Okay? So monolithic operating system has some problem, and this one says, well, if we have to redesign the entire operating system, what will we do? Okay, and over here we sort of mentioned that there are, I guess in this book chapter, we cover two possibilities. One is called virtual machine, and these days virtual machine is very popular. We're doing our kernel assignment inside virtual machine for some of us. And if you go to job interviews these days, lots of people are using virtual machines. Okay. The other one, not so popular, is called microkernel. So we're going to sort of briefly look at microkernel. We're going to spend most of today's lecture on virtual machines. All right. So why do we like monolithic kernel? Okay. Monolithic kernel great is because it's really fast. Okay. So a monolithic kernel is sort of the fastest way to go. People have tried when they do operating system research other approaches. But then, they all found out that other approaches are just too slow. Okay, so eventually they throw everything back in the kernel, so the kernel is very bloated. All the device drivers are in the kernel. Should the device driver be in the kernel? Well, they're doing, privileged instructions and stuff like that, I/O and stuff like that. So yeah, so they are supposed to be in the kernel, but people try to move them out. Okay, so why do people try to move them out, right? It's because even though when they're in the kernel, they have very good performance, but also they're the one that crashes the kernel. Okay, Microsoft Windows had a really, really poor, reputation in the 90s and the 2000s because the operating system crashes all the time. You probably heard of something called the blue screen of death. Most likely, when Microsoft Windows died, it's because one of the device driver crashed the operating system. Okay, so if you think about things that are executing in the kernel, right? There are things that the operating system vendor can control, and then there are all these drivers that get plugged into the kernel. If those things die in the kernel, they mess up other kernel data structures, while the entire operating system dies. Okay, so the major problem with the monolithic kernel, right, putting everything inside the kernel, is reliability. When you have bugs in the kernel, it makes the kernel look really bad. Okay, so what is the solution to this problem? Okay, the solution to this problem is to move everything outside the kernel. Okay, if you only have people for Microsoft Windows, if the only thing that are in the kernel are the stuff that are done by Microsoft, okay, then chances are you're going to have less kernel crashes. Okay, you still might have driver died, but if the driver can be moved to user space, which of course, well, how does driver goes into user space? It's a little weird. But if we can put the driver in user space, then when the driver dies in the user space, well, at least it doesn't crash the operating system. Okay, so that's the basic idea. You want to put stuff out in user space so they don't take down the operating system when they die. Okay, and there are two approaches to do that. One is virtual machine, and the other one is microkernel. All right. Okay, so over here it says, I guess basically this is what I said before. So the idea here is that you want to provide the kind of isolation that's provided by the operating system. Right? What kind of isolation does the operating system provide? What it provides for the user application, so the user application don't interfere with each other. Okay. Also, the user application does not interfere with the operating system. Okay. We want the same kind of isolation inside the kernel. Okay, the kernel are divided into subsystems. What if we can say that the subsystem cannot corrupt each other? Wouldn't that be great? Okay, then you have a lot more reliability, right? So you have subsystem for device driver, so they cannot corrupt your scheduler or your other important part of your kernel functions. Okay, so the question is that how do we really provide something like that, inside the kernel? All right, we're going to look at virtual machine, and this is really old technology, 45 years ago. And these days we sort of have a different motivation. So virtual machines are really, really old technology. IBM wants to build. Okay, I mean at that time, 1964, there's only IBM pretty much. Right? IBM wants to build a multi-user time-sharing system. Okay, they started a huge project called a time-sharing system. So as it turns out that they found out that it's a very, very difficult system to build. Okay, they want to build a large monolithic system. They put lots of people on it. Okay, they did it for many, many years, and eventually the project is a complete flop. I think the project lead for this project, his name is Fred Brooks. After this project died, he wrote a very famous book, and these days they're studying in the business school. It's called The Mythical Men Month, right? So the idea over here is that if you want a project to be done in half the time, throwing twice as many software engineers on it, it's not going to cut it. Okay, I mean, these days we sort of take it as an obvious thing, right? The more people we put on it, doesn't mean that it's going to complete faster. Okay, is that why your kernel can only have 4 partners? I don't know. All right. Anyways, so then IBM sort of find out that or somebody realized that IBM already have a single user time sharing system. Okay, so they want to build a multi-user time sharing system. What if you can just take this code and put it on a machine where you can run multiple instances of CMS, the single user time sharing system? Don't you end up having a multi-user time sharing system? Okay, so you have an operating system. What you want is to have this operating system run on top of another operating system. Right? That's all. Right? Then you can actually implement this thing. Okay, so this is something called the virtual machine monitor. Okay, that can support multiple operating systems. Okay, something called CP67. Right? So in this case, if you can build this thing that support multiple virtual IBM 360s, I mean, these are gigantic machines, but we can sort of support them as a virtual machine, sort of a fake machine. Okay, if we put it together, then we solve what the IBM people want. All right, so that sounds like a really simple solution, right? All you need to do is to put, put these things together. Okay, so this is the operating system. This is the CMS, the single user, operating system. And if you put multiple of them running on one piece of hardware, okay, and use the virtual machine monitor technology to switch between these operating systems, then it's done. Okay, so by the way, the term monitor in operating system that means that it's a synchronization construct, okay, that allow executing entity to have both mutual exclusion and the ability to wait for certain condition to become true. Well, so it is an operating system, right? Inside the operating system, you multiplex between a bunch of user processes, and you let user processes to wait for things to happen inside the kernel. Normally operating system is, acting like a monitor. Okay, so this is not a hardware monitor. This monitor is this OS synchronization, construct that allow multiple operating systems to run on top of it. Okay. So in this case, right, if you look at this picture, the user application will be running on these, single user time sharing system, okay, the CMS. The CMS is going to be sitting on this thing, we call it the virtual machine. Okay, and the virtual machine, a bunch of these virtual machines is going to sitting on top of this virtual machine monitor, and the virtual machine monitor is going to run on top of the actual hardware. Okay, so over here, so just like the operating system, if you have a single processor, right, the operating system can only do one thing at a time. Okay, so therefore it can run one user process at a time. In this case, this operating system will run one virtual machine at a time. Right, so it's as if you're having a one IBM 360 running right here, and then you can switch between running different IBM 360s. All right, so over here it asks the question, what abstraction does this guy right here, the virtual machine over here, what abstraction should it provide? Okay, if you look at this picture, right, the operating system is sitting on top of this, so the operating system should think that it's running on the raw hardware. All right, so the idea of this virtual machine here is that it's as if it's acting, it's acting as the real hardware. Okay, this operating system, CMS over here, should know no difference between running on the virtual machine and running on the real hardware. Right, and that's what a real abstraction is, right? You actually can tell that, no difference. You have no idea what the hardware looks like. You just execute, and it is as if you're running on the real hardware. Okay, so we know what this interface sort of need to look like, and the question is, how do you actually build this? All right. Okay, so how do you really do this, right? So the idea over here is that you can run the entire virtual machine in user mode of the real machine. Okay, so over here, this is our virtual machine, right? We're running the user over here, and we're running, the CMS, the operating system. Okay, so over here, sometimes this guy will be called the guest operating system. Okay, because the virtual machine monitor is the real operating system, right? So you will call this the guest operating system. What's running over here will be the host operating system. All right, so the idea over here is that we're going to run operating system in user mode. Can we run operating system in user mode? Well, that's what we need to figure out. What does it take for you to run operating system in user mode? Okay, so we run the entire virtual machine, right? Over here, user processes and the operating system in the user mode of the real machine, right? So over here, sort of draw this picture. This is the real machine. Inside the user mode right here, we run the application for the operating system and the operating system in user mode right here. Okay? And down in the privileged mode in the real machine, we run the virtual machine monitor. Okay? So the VMM runs in the privileged mode of the real machine. Okay? So the VMM needs to keep track of, whether every virtual machine is in the virtual privileged mode or the virtual user mode. Okay, so over here, inside the VMM here, we need to keep track of every one of these fake machines. Is it running in user mode, or is it running in the operating system mode? All right, so it's pretty much what you are keeping track of in your kernel assignment, right? Right now, you're tapping into the kernel assignment. You keep track of a lot of user processes. Do you know what's going on in user processes? Okay, if the user processes, if the threads in that process are all sleeping, then you know exactly what state that process is, right? I mean, you don't know the one that's running. The one that's running, you don't know what state it's in. But everyone that's sleeping, you know exactly what state it's in. Okay, so over here we have the same thing, right? This is the real operating system. Inside the virtual machine monitor, you know the state of every virtual machine if that virtual machine is suspended. Okay, if that virtual machine is executing, then you don't know because the operating system is not even running. Okay, but so over here, it is possible for you to know exactly what state you are in inside every virtual machine. Okay, and that's what you need to keep track of. All right, so the OS runs in the virtual privileged mode of the virtual machine. The guest operating system runs here, and the application, runs, in the user space. All right, so again, this is the basic idea. All right, so the processor inside the virtual machine is the real processor. So what does that mean? Okay, so if you look at this picture, right, so now we have this file level, okay, we know that, this is running in the privileged mode of the real machine, and this is running in the user mode of the real machine, okay? When you run, when you execute instructions over here it says, well, the processor in the virtual machine, right, this is the virtual machine. The processor in the virtual machine is the real processor. Okay, which means that the instruction that you're executing over here, we want it to execute on the real hardware. Okay, we don't want this thing sitting below to be an emulator. Okay, what's an emulator? Well, QEMU is an emulator, right? When you run the kernel assignment, your Unix is running on top of QEMU, and QEMU is an x86 emulator. So every instruction that you execute in your kernel code is actually not running on the real machine. Okay, every instruction you're running in Unix, they're actually getting emulated by QEMU. Okay, so they are not executed. All right, in the real virtual machine, if we do that, then the virtual machine will be really slow, so that won't be acceptable. So we have to execute all the instructions over here on the real hardware. All right, so that's a requirement. Okay, but probably not every instruction, because some instruction, if you do that, you're going to be in trouble. Okay, so we got to figure out how to build this thing in the bottom layer, because this now is the operating system. So sometimes you'll have to trap into the operating system to do something you're not allowed to do over here. Okay, so what are you not allowed to do over here? Right, because right now I'm executing in user space, right? If I execute a privileged instruction in the guest operating system, what's going to happen? Well, it's going to trap into the operating system, right? Okay, so that's what a privileged instruction means, right? If you execute a privileged instruction in the user space, you trap into the operating system. Okay, so if you execute code in the user space, okay, and if you execute a privileged instruction like a trap, where do you go? I mean, you don't go into the guest operating system, right? You're executing the trap instruction, so boom, you're inside the VMM. Okay, but if you want to provide the abstraction that when you execute this instruction, you actually went into the kernel. Therefore, once you get into the VMM, you got to make sure somehow you get back into the guest operating system executing code over there. Okay, so there's this transfer of control that you have to implement so that you can create the illusion that, you know, the guest operating system is running on the real hardware. All right, so if you generate a trap, right, this application make a system call. Okay, now when you trap, you're in user mode, you trap into the operating system. Well, this is the real operating system. It's the the thing that sits around on top of the hardware. So you get trapped over here, and now when you get into the trap, how do you handle the trap? Right? I mean, think, handle page fault. Okay, you should be very familiar with that, right? Inside handle page fault, you look around to see, who actually trapped into the operating system. Okay, so in this case, we have a virtual machine monitor. We need to figure out which virtual machine trapped into the virtual machine monitor. Okay, can we do it? Well, you have to use the same kind of data structure, right? VM area and things like that. Page frame, how do you map from one place to another? We're going to use all that data structure in order to figure out, what happened. Okay, so all that data structure is basically what this layer is. All right, so just like in Unix, when you do handle page fault, you go through a bunch of kernel data structure, okay, and now you have to go through kernel data structure that belong to this machine, this virtual machine, in order to figure out exactly how do you transfer control into the guest operating system. Okay, because you want to create the illusion that this trap instruction eventually caused handle page fault inside the guest operating system to execute. Okay, so you start with handle page fault inside the virtual machine monitor, and then find the right place to transfer control into. So how do you transfer control into the guest operating system? Right, remember the guest operating system is running now in the user mode, right? This is in user mode. Okay, so again, you have to do return from interrupt in order for you to return back into the guest operating system. Okay, so therefore the picture that's drawn over here is that, you transfer control into the virtual machine monitor. The virtual machine monitor, looks through some data structure, maybe transfer control into some code into the virtual machine so that you can do a return from interrupt and go back into the guest operating system, right? Because the guest operating system is now running in the user mode. All right? So it gets a little more complicated. Non-privileged instruction, add, multiply, and stuff like that. When you execute those, either in here or in here, well, nothing happens, right? You're executing on the real machine, they just execute. And what is the virtual machine monitor doing if you only have a single processor? Well, nothing, just like a regular operating system. If the application is running, your operating system went to sleep. Okay, you're sitting there waiting for what? You're waiting for either a trap or an interrupt, right? So over here, it's the same thing. Whatever that's sitting on the hardware, okay, if you're running user application, the virtual machine monitor is sitting there waiting for a trap or an interrupt. All right, so it's sleeping, right? So all these things will execute as is inside the hardware. Okay, if you have, okay, so over here I sort of drew the picture of our kernel assignment, right? Our kernel assignment, we have application, like hello and stuff like that. They run on top of Unix. Unix run on top of QEMU, which is a software emulator for the x86 instruction set. QEMU runs on top of Linux. Linux runs on, real hardware. Okay, and this Linux, right, is Ubuntu Linux, 12.04. So the picture looks like this, but it's nothing like that. because QEMU is an emulator, while inside the virtual machine, we're actually executing instructions. Okay, so these two, it's kind of like, but it's, it's actually very different. All right, so please know the difference. All right, if you have a privileged instruction, okay, you will trap, for example, making a system call, fork, read, or write, or whatever, right? You trap into the virtual machine monitor. The virtual machine monitor look into the data structure in order to figure out how to deliver that trap to the guest operating system. Okay, eventually it figure out where to transfer that control to. It does a return from interrupt, and then the guest operating system start to execute. So as far as the guest operating system is concerned, it's almost like this. What's happening below is the hardware abstraction layer. Okay, you just got to trap, somewhere in the hardware abstraction layer. Eventually, make it go back into the trap handler. All right, so you can sort of imagine that this can actually be done. All right. Okay, most instructions that are executed inside the guest operating system, what kind of instructions are they? Are they privileged instructions? Okay, think about your kernel 1 and 2 code, right? The kernel 1 and 2 code, is there any code that's privileged? You're adjusting linked lists, pointers, and, move things around. Maybe none of them are really privileged. Okay, so most of the time, so this looks slow, right? You're transferring control into the, into VMM, and then do a return from interrupt. So it's like you're going from user space to kernel space, go back to user space. This is really slow. Okay, if this happened all the time, then your machine is gonna, behave, run really slowly. Okay, so luckily, most of the time, most of the instructions that you run in the operating system, they're really not privileged. Okay, adjusting data structure, they are not privileged at all. Okay, there are certain instructions that are privileged when you do an I/O operation, when you change the page table location, well, those are privileged. Okay, but most of the stuff that you do are really not privileged. So, in order for you to decide what is privileged or not, you actually have to go through every instruction that's supported by the hardware and analyze it carefully to make sure you understand whether it's privileged, it should be privileged or not, right? Push EBP, should it be privileged? It's not, right? Well, as we know, every function get compiled into the first thing is push EBP, right? So clearly that's not that's not a privileged instruction. All right. So let's talk about these, special instructions that you really need to sort of handle with care. So there's another name for it when we talk about virtual machines. These are called sensitive instructions. Okay, the sensitive instructions are the one that must execute in privileged mode, which means that if you execute them in user mode, you will trap into the operating system, and the operating system can handle it. Okay. Over here, we try to sort of distinguish between, privileged instructions, and sensitive instructions. The sensitive instruction is an instruction that will change something in the actual hardware or the processor. Okay, so one of the examples that we use is that, this is the instruction that can change the mapping of virtual to real memory. Okay, so for example, in x86, right, if you change the content of the CR3 register, what happens when you change the content of the CR3 register, right? So CR3 register contains the physical address of where the page table is. Okay, so think about this picture, right? Over here, if I'm running a sort of a guest operating system, okay, and this guy is going to set the CR3 register. It says CR3, okay, gets 0x, something like that. Are we allowed this guest operating system to change the CR3 register? What if we actually allow the guest operating system to change the CR3 register? What's going to happen? All right, it's going to mess up all the other virtual machines, right? Okay, because this CR3, the CR3 sort of is a virtual, it's a virtual register, right? It shouldn't be the actual register inside the hardware. Okay, inside the hardware over here, there's a real CR3 register. It points to the page table. Okay, for a user process. Okay, if you allow the guest operating system to actually change the CR3 register, then all the other when you switch to running another virtual machine, okay, what happens is that you're basically going to mess up the VMM. Okay, only the VMM is allowed to change the real CR3 register. Okay, when this guest operating system changes CR3, it should be changing the CR3 register inside the virtual machine. All right, so over here, I guess that's why this is also called a virtual machine, right? Because every one of these, registers that are special related to hardware mapping, well, you sort of have an image inside the virtual machine, okay, that they represent the real hardware's, register. Okay, so for example, maybe the code, I guess on Intel, I guess probably shouldn't talk too much about Intel. There are things that are like the segment descriptors. Okay. Anyways, there's some other registers that belong to the hardware. Is that when you try to modify them, okay, you got to make sure that there's an image inside the virtual machine that's the one you modify. Okay. This way, when your virtual machine goes to sleep, you will record all that information from the hardware, copy them into the virtual machine. So later on, when you try to run this virtual machine again, you're going to restore all these things into the hardware before you return from interrupt. Okay, so this way, when you continue to execute, you will be having the correct machine state. All right, so same thing with other virtual machines. Other virtual machines also have their own set of register. Right, so this is, again, is very similar to our kernel assignment. When you trap inside the operating system, there's a bunch of register that you save inside the kernel for that user process. So later on, when you return from interrupt, all that processor are stored inside the context, inside the process control block. They are the one that needs to be restored into the processor before you return to that user process. Okay, now you scale one level up. Now you have these processor for a particular, you have these registers for a particular machine, and those are the information that you need to restore before you continue to run that particular virtual machine. All right, so things like CR3, those are the ones. So when you try to modify CR3, that instruction is known as a sensitive instruction, and the sensitive instruction has to be also privileged. Okay, similarly, if you want to provide run an I/O operation, right? Intel has an instruction in 23. You try to read an I/O, register, or try to read an I/O device, or out, 58, right? Try to change a particular piece of hardware. Okay, can you execute this instruction inside the guest operating system? No, right? Because it's going to mess up the hardware. Okay, so again, when you try to execute these kind of instruction, you have to trap into the VMM, and the VMM has to, can VMM execute this instruction for you? No, it can't, right? Because, because otherwise it would be the same as you executing these instructions. So, when you do these kind of instructions, because you think you exclusively own the hardware, right? But in this case, you're sharing the hardware with all the other virtual machines, so you cannot do things like this, just as you cannot change the CR3 register, directly. Okay? So in that case, when you trap into the VMN, what the VMN has to do is to emulate that instruction for you by making these modifications inside the virtual machine and not inside the real hardware. All right? So over here, it says the VMN emulate, these sensitive instructions. All right? Okay, so a privileged instruction must be, a sensitive instruction must be privileged. Right? Why is that? Okay, because if you're allowed to execute I/O operation or change the CR3 register inside the guest operating system without it being privileged, then when you execute that directly in the guest operating system, it will just go ahead and do it. Okay, you will not trap into the VMM. Right, because right now this thing is running in user space, and this is running in, in the privilege mode. So if you execute I/O instructions, or if you change the CR3 register right here, well, if it's not privileged, then it will execute just fine. All right, so that will be the wrong thing to do. Okay, so therefore, these sensitive instruction has to be privileged instructions, so that if you try to do these operations inside the guest operating system, you will trap into the VMN. All right? So what if they're not? If you have a sensitive instruction, okay, that's not privileged, then it will execute inside the guest operating system, and you will end up changing the wrong CR3 register because you will change the one in the hardware and not inside the virtual machine. Okay? Then the claim over here is that you cannot build a virtual machine for this particular processor. All right, so it's very important that the sensitive instruction needs to be privileged. Okay, otherwise all bets are off. You have to use a different technology. All right, we're going to come back to this a little bit later to say how to get around this particular problem. Okay, but for now, I mean, if you execute, a sensitive instruction in the guest operating system, it will just execute and that will mess everything up. Right. Another thing that you have to take care of is I/O. Okay, so I/O is done using memory map I/O or with I/O instructions, right? You're talking device register. But what about, the actual, things like disks? Okay, so for example, you try to do a read from the disk, right? And again, we have multiple virtual machines right here. Okay, every one of them thinks they own the entire disk, right? Because we're virtualizing, the entire hardware to make it think that they own the entire hardware. Okay, so therefore, what we would do in virtual machine is to take the real hard disk and basically divide it up. Depends on how many virtual machines you have, and say that, well, this part of the disk belongs to this virtual machine. Okay, so this way, when you're trying to deal with the disk, okay, you end up, you have to deal with the virtual disk that's inside over here. Well, there's really no disk. Okay, there's just some data structure that pretends that it sort of looks like a disk. Okay, so in that case, when you try to perform a read, what happened, right? Read will get, I don't know if that's the next slide. Okay, so when you try to perform a read of that particular disk, okay, what end up is that you think that you're reading this particular disk, but that read operation is going to get trapped into the virtual machine monitor. The virtual machine monitor is going to look up the data structure inside the virtual machine and then, finish that operation and then transfer data to the right place as if a read has been performed. Okay, so in that case, what it needs to do is that, this read, when it, so I guess, how do you do a read, right? Eventually, you have to invoke the device driver, and the device driver is the one that's going to do the read from the disk. Okay, so when the device driver read from the disk, it might use a memory map I/O instruction, so actually use an I/O instruction to talk to the device controller. Okay, so at that point, you trap into the virtual machine monitor. The virtual machine monitor is going to actually emulate that particular instruction for you by transferring data from the real disk into the virtual disk. Okay, and then transfer control back into the operating system to simulate the interrupt, the disk completion interrupt, to make the code over here execute to think that the data has been transferred into a particular location inside memory. All right, so again, the VMM has to make all these things happen, making the operating system think that it actually is talking to a real disk. All right, so this one you can sort of see that it needs to understand how a device driver works. Okay, because over here we have a device driver that needs to talk to the disk. So this guy sitting down here, the virtual machine monitor, is actually very smart. It knows about all these devices, right? Because it's simulating, it's simulating a virtual disk using a real disk. Okay, what about all the other devices? Okay, the keyboard, the monitor, the mouse, other kind of, camera and stuff that you plug into the system. Okay, every one of these I/O devices, the virtual machine monitor needs to be able to, have a data structure over here inside the virtual machine to have a virtual camera, to have a virtual mouse, to have, virtual devices all over the place. Okay, so this guy's getting more complicated, right? In the beginning, we try to take all these stuff outside the operating system so that, the operating system kernel is nice and small. But now when we need to deal with I/O, things get a lot more complicated. Okay, so it's really not easy to build a virtual machine. Okay, so IBM, was very successful because IBM is the only vendor. They don't have to worry about these, devices. They control, pretty much anything. And once they start getting the virtual machine to work, they actually realize that virtual machine actually has a lot of other benefits. Okay, so over here, this one sort of tell you some of the benefits of the virtual machine. We're going to talk about this first before we talk about how to really solve all that I/O problem and also, the sensitive instruction problem. All right, this is sort of a good technique to structure the multi-user system. Okay, it has many advantages as they found out. Okay, one is that if you can actually ship a virtual machine to your customer site, you can actually do debugging on a sort of so the customer will be using one virtual machine because the virtual machine will run exactly like the real the real machine. And now you can actually have another machine sitting right next to it, which is a copy of that machine. When the customer is complaining about a particular bug, you don't have to replicate that entire machine, at your engineering site. You can actually just replicate that particular machine on exactly the same piece of hardware. Okay, you can actually use debugging right on that piece of hardware. Okay, so that's that's a major advantage. And also, if you want to make adding a new feature, you can add a feature on that on a different virtual machine on that same piece of hardware. And when you finish testing, you can just say, "Hey, customer, it's ready." You just switch to the other virtual machine. Okay, so the customers sort of really like that kind of idea that they don't really have to rebuild a new machine or going through the trouble of loading a brand new operating system, because the new operating system is sitting on the same machine already. All they have to do is switch to running a new virtual machine. We can also make hardware modification inside hardware. Okay, if we want to change the processor, add a new machine instruction, or add a few features inside the hardware, well, now it can be done. Okay, with virtual machine, right? If you have an instruction that doesn't exist, okay, if you think about all the x86 instruction set, right? They have all these instructions. If you want to add a new instruction, well, if you execute that instruction, you're going to trap into the operating system, and you're going to get the exception as being invalid operation code. You're going to invalid opcode because that instruction doesn't exist. Okay, so what's going to happen inside a virtual machine if you do something like that? You'll trap into the virtual machine monitor, and the virtual machine monitor can emulate that instruction. Okay, so even though that instruction doesn't exist in the current machine, you can emulate it in VMM. So later on, when you finish building a new machine, you can just say, hey, it's already running in this machine because this machine is emulating, because the abstraction it provides is the new hardware. So when you switch to the new machine, everything should run as is. All right, so you can actually use this to, to easily add, hardware to your current machine. You can run different operating systems on the machine, and these days, that's one of the reasons that virtual machine is very, very popular now, is because of cloud computing. Okay, I guess Amazon, and I guess there's these public and the private cloud and stuff like that. Microsoft have their own cloud. So the idea of some of these cloud is that on one virtual, so on one of these real machine, you can run multiple instances of virtual machines, and every virtual machine can be configured differently. So on, so let's say that this is one of the sort of cloud computing. You have one piece of hardware over here, and inside over here you run a Windows system, and then over here you run Linux, okay, and over here you run a slightly different Linux, and over here you run a different version of Windows, okay. All these different operating systems can run on a single piece of hardware. All right, so this is sort of responsible for the big boom in cloud computing, these days, is because now you can run all these things onto the same machine. Okay, so again, I really haven't talked about, the solution to make these things run, and that's going to be the thing we're going to look at next. All right, so the virtual machine, so there are two ways to build virtual machines. Okay, one is called pure virtualization, is that you virtualize everything, right? The operating system that you run, okay, cannot tell whether it's running on a virtual machine or the real hardware. All right, so as it turns out that you have to virtualize processor, you have to virtualize memory, you have to virtualize every device on your hardware, and then every I/O devices that are connected to your machine. Okay, so this is called pure virtualization, and it's very costly. All right, another way to go is called para-virtualization. All right, so in this case, the virtualized entity, the guest operating system, is a bit different from the real entity. Okay, so remember, I guess many people are using VirtualBox to run Ubuntu Linux, right? When you run Ubuntu Linux, do you run a different version of Ubuntu Linux if compared to people who are running on the raw hardware? We don't do that, right? We take the ISO file, download it from the Ubuntu website, and we just run that into the virtual machine. Okay, so in that case, we are doing pure virtualization, right? Because we don't modify the operating system at all. We run it as is. Okay, for parallel virtualization, the virtualized entity is a bit different from the real entity. The real entity is the .iso file that we download from from the internet. Okay, so this one is that it's a different ISO. Okay, it's a different version of the operating system. This operating system is actually designed to run inside a virtual machine. Okay, why would you want to do that? Okay, so if you go back to this picture, or maybe this picture, okay, if you're running in the cloud, okay, and you can plug into this, the system over here, and you don't really want to worry about all the I/O devices that you plug into it. Okay, maybe you're willing to rewrite all your device drivers. Okay, maybe you are willing to only allow a certain device driver to run inside your operating system. So you have a specialized version of your operating system. Okay, so this window will be different from the window that you buy, from Dell. Okay, but this one you can run inside you can run inside a virtual machine. Okay, and also the picture that I showed you before, right? When you execute a sensitive instruction, you got it down into the kernel. You go look up. You come back into the guest operating system. That's kernel to user and user to kernel, transfer, and that's slow. Okay, now you're working on kernel 3. Does that happen a lot? Okay, if you set a breakpoint to handle page fault, how often does that happen? Well, quite a bit. Okay, I mean, you're trapping the operating system all the time. Okay, and we still have reasonable performance. Okay, but the more you do that on every I/O instruction, if you start doing that, then that's why you want the device driver to execute in the kernel, because you don't want to go up and down, from user space to kernel space. So when you're dealing with the device, if you have to go up and down very, very often, then you're going to end up with a very slow system. Okay, so if you plug into your cloud, okay, you have a machine you want to run, in the Amazon data center. Okay, maybe you're willing to take out your device driver and put in something special so they can run super fast inside the cloud. All right, so those things are called para-virtualization. Okay, you modify your operating system so that it can run inside a virtual machine, very efficiently. Okay, you try to go as few times between transferring control to the VMM and coming back as much as you can. All right, so let's talk about how to build a virtual machine. Okay, so as it turns out that in 1974, Popek and Goldberg, they wrote a paper to try to figure out. They're at UCLA. They tried to build a virtual machine on Intel, and they found out they couldn't. Okay, and they tried to find out why they couldn't build a virtual machine on Intel. Okay, as it turns out, it's the sensitive instruction. If there's a sensitive instruction that's not privileged, well, you can't build a virtual machine. Okay, they will actually be able to prove it inside a paper that they published in 1974 to saying that the sufficient condition to be able to construct a virtual machine is simply one very simple rule, is that a computer set of sensitive instruction is a subset of the privileged instruction. Okay, or every sensitive instruction has to be a privileged instruction. Okay, so this way, when you execute the sensitive instruction in the guest operating system, you guarantee to trap into the virtual machine monitor. Okay, because if you're not be able to do that, then the wrong thing will happen, and then therefore you cannot construct a virtual machine. All right, so this theorem holds for IBM 360, and how do you know? Well, you have to go through every machine instruction, analyze the heck out of it, and make sure that every sensitive instruction turns out, to be a privileged instruction. Okay. This theorem does not hold for the x86 processor. So in 1974, they declared that you cannot build virtual machine with Intel. All right. So this is true for the next 20 years. Nobody built a virtual machine for Intel because it was proven mathematically that is not possible. Okay, until somebody until VMware come up with a solution. All right. So applying that theorem, to this picture, okay. If you look at the real machine, okay. If you have a non-sensitive instruction, add, multiply, and stuff like that, it doesn't really matter if you're in the user mode and the privilege mode. They will execute, just as normal. Okay. If you have an error instruction, okay, then in user mode you will trap into the kernel. If you have an error, if you run in the privilege mode, what happened? Right? I mean, right now we're doing Unix, right? We know that this is not supposed to happen, But if it happened, well, you get a fault inside the kernel, but you can still handle it, right? Okay, in Unix, we have code to say don't handle it. If you get a page fault inside the kernel, the code that you're not allowed to modify, well, that's the one that crashes the kernel. But if you really want to handle it, you can actually handle it. Okay, so if you execute like a page fault or something like that, the normal action when you're in the privileged mode is still to trap into the kernel. Okay, if you have a sensitive instruction, if you're executing the user mode, okay, in that case you will trap into the kernel. And if you're in the privileged mode, if you execute a sensitive instruction, it will execute just fine. All right? What about in the virtual machine, right? So let's focus on this one, right? This entire thing is executing in the user mode. Okay, now if you're building a virtual machine, what do you have to do? Or you're building a VMM. When you have non-sensitive instruction, if you're executing over here in the user mode, where they execute fine. If you're executing in the privileged mode, they also execute directly on the hardware just fine. If you have an error instruction, okay, like a page fault or something like that, divide by 0, right? Then in that case, what you need to do is that you need to transfer control into the corresponding trap handler inside the guest operating system. Okay, so in that case, the VMM is not emulating this instruction. The VMM is like the picture that we drew before, right? You transfer control, transfer control, transfer control. You want to execute code back into the guest operating system. Okay, so you trap into the VMM. The VMM causes trap to the guest operating system. All right, and this happens whether you are in the user mode or in the privileged mode inside the virtual machine. Okay, and finally, what about the sensitive instruction? Okay, if you execute a sensitive instruction in the virtual user mode, which means that this code right over here, okay, if this is executed as a user application, okay, then this operating system knows how to handle those kind of exceptions. Okay, so therefore, if you're in the virtual user mode, when you execute a sensitive instruction, you're supposed to transfer control into the guest operating system. Okay, but if the sensitive instructions are executed in the guest operating system, then what needs to happen is that the virtual machine needs to emulate these instructions. All right. Okay, so let's talk about Intel and what is the problem. Intel is not the same as IBM, even though if you look at the hardware, they're very similar. A couple of main things that are different. Number one, IBM, the way they do I/O is they're done through channel program. Okay, and the channel program talk to the channel. I guess we sort of saw one slide before about these channel devices. They're the I/O devices that are connected to the mainframe. And you talk to them as if you are going through a communication channel, right? That's why they're called the channel, sort of the channel device. Okay, so talking to the devices are very uniform. Okay, and that's how it's done in IBM. Okay, in Intel, the I/O devices, they're all done through memory map addresses, and all different vendors sort of deal with all these kind of stuff differently. So for Intel, this is a big mess. What about the sensitive instruction? For IBM, all sensitive instructions are privileged instructions, right? So that's why we can build a virtual machine, okay? For x86, the major difference over here is not all sensitive instructions are privileged instructions, okay? So that's why we declare that you cannot build virtual machines for IBM x86. Okay, as it turns out, there's only one bad instruction, okay? If you analyze every Intel instructions, okay, you find out only one of them is going to cause this problem. So if we can only fix one of these instructions, and then we're home free, and we can start building virtual machines for Intel. Except we have to address also this problem, because this problem is going to kill the performance of a virtual machine. Okay, and also it's going to be a lot of work to implement a virtual machine. All right, so Intel processor has 4 rings. Okay, it's called ring 0, 1, 2, and 3. Right over here is 0, and over here is 3. The kernel, so it turns out ring 1 and 2, most people don't use it. Okay, the kernel runs in ring 0, and the application runs in ring 3. So basically, this is the privileged mode, and this is the user mode. Okay, so in that sense, it's again very similar to IBM. Okay, what's mainly different about Intel is that there's this instruction called pop flags. Okay, pop F is like pop EBP. right? What does pop EBP do, right? If you have a stack over here, and here is ESP, right? Inside the CPU over here, this is CPU, right? Over here, there's ESP and there's EBP, okay? ESP point to somewhere on the stack, okay? Pop EBP says, take the top of stack and put it inside the CPU's EBP register. All right, so that's pop, EBP. Right? Push EBP is push, the content of EBP to the stack. Okay. Similarly, there's an instruction called pop flags, is to take the top of the stack and treats them as an array of bits that are the CPU flags. Okay, what are CPU flags? CPU flags are like, overflow, carry, things like that. When you perform arithmetic operation, if there's an overflow, the overflow flag will be set inside the CPU. When there's a carry, the carry flag will be, set so that you can perform arithmetic operation. Okay, there's a bunch of flag over here. There are actually other flags like interrupt, enable, and stuff like that. They're part of the CPU flags. Okay, so pop F will take the top of the stack and then, put it into all these flag register all over inside the CPU. Right, so remember the first time when we look at the x86 CPU, the register called the flag register. Okay, so the pop flag take the top of the stack and then, restore them into the CPU. Okay, how did this thing get into the, get onto the stack? Well, there's a corresponding push flag, push F instruction will take all the CPU flag and push them onto the stack. All right, so this is part of the context of your thread, right? So when you want to restore your thread, you need to pop all the flags back into the CPU, and then, your thread is allowed to continue to execute. Okay? So the trouble with pop flag is that it behaves differently in user mode and in kernel mode, and it's not a privileged instruction. Okay, so the Intel processor was actually built so that if you execute pop F in the kernel mode, this entire thing will go onto the CPU. Okay, it will go to the corresponding bits and set all these bits inside the CPU. Okay, but if you execute pop F in the user mode, only some of the bits will get used, and the other bits will be ignored. Okay, so for example, some of the bits over here are interrupt enable, okay, which kind of makes sense, right? If you're in the user mode, you say, pop F, restore the flag from the top of the stack into the CPU. Well, you don't want to change the interrupt enable flag because that's a privilege operation. Okay, so unfortunately, the Intel was designed so that they use the same machine code for doing this in the user mode and in the kernel mode. Okay, if the Intel designer were smarter, back in the 60s, what they would have done is they would have done two different pop-F instructions, one for doing in the kernel mode and one for doing in the user mode, and the kernel mode will be privileged and the user mode will not be privileged. Okay, but unfortunately, they didn't design it that way, so when you execute this instruction's behavior depends on the CPU mode. Okay, if it's in the user mode, only several bits will be restored in the processor. If you run this in the privileged mode, the entire, flags will be restored into the CPU. Okay, so why this doesn't work inside the virtual machine? Right, because if you're inside the kernel and you execute, pop F, okay, now the kernel in the guest operating system is executing user mode. Okay, so therefore, you are not setting the interrupt enable bits inside the processor, so it does the wrong thing. Okay, so if you execute this instruction inside the kernel, the wrong thing happens. Okay, so this instruction is supposed to be privileged, and it's not, and that's why, Intel, you cannot build virtual machine. So if we have a way to fix this, then we're in good shape. Okay, so how do you fix this, this problem? So, in the 1990s, VMware come up with a solution, to fix this thing. Is that the next slide? All right, so here are some of the solutions to this problem. Number one, this is what VMware does. It's called binary rewriting. Okay, you rewrite the kernel binaries of the guest operating system. Okay, the guest operating system .iso file, as you install into the operating system, it's installed as is. But as you start fetching these instructions from the operating system, you go around and you modify the operating system on the fly. Okay? Every time you see a pop-up instruction, what do you change it to? You change it to an illegal instruction. Right? If you change it to an illegal instruction, when it executes in the user mode, in the kernel mode, you will trap into the VMM. Okay? The VMM can change that. Say, oh, why you want to do pop-up? Are you in the user mode? Are you in the kernel mode? And you will do the write operation. It will emulate that particular instruction. Okay, so if you can do that on the fly, and you know, VMware figured out how to do it, right, using dynamic binary rewriting. Okay, so if you think about, I mean, what does that mean by dynamic binary rewriting? Okay, it's related to the code segment, right? So if you think about what you're doing in Unix, okay, I guess the V node, the memory map object over there, when it does a fill page, okay, maybe you can change popf into something else. Okay, but it's a little bit tricky, right? Because you know, popf has a certain machine instruction. That machine instruction could be, you know, some sort of a, argument inside another instruction. Okay, so you have to find the instruction boundary to determine exactly where the operation code is in order for you to substitute that, for the illegal instruction. All right, so anyways, I'm just saying that, you know, it's not that straightforward. You just change, fill page, and then, and then everything's done. Okay, you have to be very, very careful and to switch out, the correct popf and replace them with the illegal instructions so you can trap into the VMM. All right, so you don't need to modify the guest operating system as they install, into your system, but you have to modify them on the fly. All right, so that's one way to do it, right, 20 years later. The other way is to fix the hardware. Okay, you have a hardware that's not virtualizable, right, the Intel processor. Well, come up with a new Intel processor. Okay, so we're going to briefly look at how this is done. And then number 3 is that you can do para virtualization, take out all the popf from your operating system. Okay, change them into illegal instructions so that they get trapped into the virtual machine monitor. All right, so in this case, the virtualized entity is different from the regular one because you take out all that code. Right, so para virtualization certainly works by taking out the popf code inside the kernel and replace them with regular instructions. The popf code inside the user space, you don't have to do anything to them. Okay, it's the one that inside the kernel needs to be modified. All right. By the way, when people use parallel virtualization, they often call the virtual machine monitor the hypervisor. Okay, so the hypervisor is the real operating system on the real machine, and pretty much people will use it interchangeably when they use the word hypervisor to mean the virtual machine monitor. Okay, so those two terms are interchangeable. All right, when you do parallel virtualization, if you're allowed to take out all the popf code from the kernel, then you might as well change everything else, right? Because once you're allowed to not use the original ISO file from the operating system, you can, why don't you take out all the I/O code, take out all the device driver code, take out everything, have a new operating system, right? So, parallel virtualization actually, once you decide to modify the operating system, you can modify the heck out of it. All right, so we're gonna, talk about that soon. All right, the binary rewriting is VMware patent. So if you look at, I guess you could go to the website, look at the top, most valuable patent in the history of technology or something like that. I mean, this patent is way up there, right? It's worth a lot of money to VMware. And then, the Google patent and stuff is also up there. All right, how do you fix the hardware? Okay, so, Intel has this thing called the Vanderpool technology. I think there are, some of your CPU on your laptop, they have this. So when you boot your hardware, you can actually look to see if they support this. When you log into your machine, if you run the command dmesg, okay, so this thing is display all the debugging messages as the operating system boot. You can actually look for VTX to see if your operating system support, if your hardware actually detected that it has the Vanderpool technology. Okay, so in the Vanderpool technology, basically it's a technology for building virtual machines, right? So normally you have user, and this is in ring 3, right? You have the kernel that's in ring 0. Okay, now for VMM you have a ring -1. Okay, they basically add another ring below ring 0, and this is where you implement VMM. Okay, what you can do is that when you boot the machine, first you have to boot the VMM, and inside the VMM you can configure so that that when you execute certain instruction, it will force a trap to the VMM. All right, so over here you can specify that when I see popf, okay, trap into the VMM. Okay, trap into ring -1. Okay, so basically you can use a bunch of configuration file, and this operation in the vendor pool technology is called VM exit. Okay, so when you see these instructions that are specified in this configuration file, you will trap into the VM. You will trap into the VMM. The VMM will execute the corresponding code to emulate all these operations. All right, so so you can emulate page file, changing the CR3 register. You can put all that list inside the configuration file over there, so you can easily build a virtual machine monitor. All right, and the requirement is that no other code should be using ring -1, and ring -1 is called the root mode, okay, or the VMM mode. All right, so that's how you virtualize the CPU. Okay, so what about the other major problem, the I/O problem? How do you really get around that problem? All right, so let's look at the real machine operating system architecture. Okay, it looks like this, right? You have a lot of physical devices. Here's the operating system. So over here, this is the hardware, right? This is the operating system layer, and this is the user space. Okay, inside hardware, you have all these devices, and you have device drivers that are used to talk to the devices. Okay, so now if you virtualize this entire machine into a virtual machine, what does it look like? Okay, so basically now you have VMM underneath, right? And underneath over here, you have the real hardware, and the real hardware has a real device. Okay, so over here, this becomes a part of the virtual machine, right? All these things over here, you need to provide abstraction for your devices. And every device that you need to abstract away, you need to provide some sort of a data structure inside the virtual machine to represent them. Okay, so therefore now the picture looks like this, right? This is your old machines over here. This become virtual devices, and now over here you have virtual processors, and you have virtual CR3 registers over here, etc. Okay, so now the real picture looks like this, and now here the real operating system we call it VMM, and inside here is where you have the real device driver that knows how to talk to the real devices. Right, the real devices could be the disk, could be the mouse, could be the keyboard, could be the camera. They're all sitting right there. Okay, so the big question is, who are writing the device drivers right here? Okay, so if you think about how many devices does Windows support? Now, gazillion, right? There are tons of devices, so many different manufacturers for webcams, for keyboard, for mouse, and stuff like that. Okay, so if we want to have keyboards and mouse connected to this hardware, do we have to write device drivers for all of them? Yes, we have to, right? Because if we want to talk to them, well, I have to have device driver. So, for the gazillion devices that we need to plug into this machine, we need to have device driver for all of them. Who's going to write it, right? If this is the machine that's sold by Amazon, okay, Amazon got to write, they're going to be in the business of writing device drivers for, 100,000 devices. They don't have the manpower to do that. Okay, so this is a problem for people who build virtual machines, is that now you figure out how to virtualize the processor. What do you do with IOs? So one solution is to say, well, we're only going to write a few. Okay, and then, well, which one do you write? Okay, so for example, if Amazon, they are in, they provide, cloud services. They have data center. They have tons of machines, tons of virtual machines. Those are all very high-end machines. So basically, they're running a server farm. Okay, in the server farm, they're operating by Amazon. Amazon can pick and choose what device they want to install onto this hardware. Okay, so they don't have to support 100,000 devices. They only have to support the one that they're gonna purchase. Okay, so over here for a data center, okay, or for a server machine, there tend to be high performance. You only have to support, maybe 20 devices, maybe 50 devices. Okay, then big companies like Amazon, they can hire programmers to write device drivers for their special hardware that can support a virtual machine, and to write this 20 or 50 device drivers. All right, so this can be done. Okay, so the question is, what about low-end machine? Your laptop and stuff like that. Okay, who's going to write the device driver for your laptop? Right? You don't really pick the device, the hardware device that comes with your laptop. Okay, so you're just stuck with whatever you have. Okay, you might plug in some USB, devices, but those will be, separate device drivers. So if you want to support them, you got to write device driver to put them inside a virtual machine. All right, and this is, again, where VMware come up with their solution. Okay, the VMware solution is to say that, well, we're going to use the Windows device drivers. Okay, this operating system sitting down here is not going to be the VMM, it's going to be Windows. Okay, or if it has a Linux host, this will be Linux. Okay, so the idea over here is that we start with a generic operating system, a popular one you can just download, you can just buy, right? Windows and Linux. They come with all the device drivers. You can plug in all these devices in there. The VMM will only go inside over here and become a driver inside that host operating system. So this is called a host operating system. Okay, the host operating system has all the device drivers. Okay, you write one additional device driver, and device driver is a component you can plug into the kernel, and that's going to be your VMM. Okay, you're going to register events with the operating system to say that, when these kind of things happen, and the operating system will allow you to do that, you can say, when this thing happens, transfer control into my device driver. Okay, so now when you're executing in the virtual machine, when certain operation happen, instead of going into the Windows, it will go into the Windows operating system, but then the Windows operating system is going to pass control over to the VMM right here, and the VMM is called a VM driver. All right, so inside over here is where you have to simulate, the devices and stuff like that, but now you don't have to implement this device driver. Okay, so now you get to change this virtual device driver, and what you need to do when you try to emulate that is that you need to make calls to the device driver from here. Okay, so if you modify your virtual machine monitor and you talk to the device driver, so again you have to interact with a lot of device drivers. So what VMware does is they come up with another solution. It's basically using the same idea as the window manager. Okay, remember, where's the window manager? The window manager sits in the user space, and the window manager can talk to all the devices, and then it can take all the events coming from your devices and then send it to all the applications that are running in the machine. Okay, so you do exactly that. They have something called a VM app over here. So this is the VMware application for dealing with a virtual machine. Okay, so this guy is the one that's actually going to talk to all the real devices. It's running as an application, and the application already knows how to talk to all the devices. Okay, so instead of for the VM driver to talk to these device drivers directly, it will go through, okay, from the kernel level, go back into the application space, and come back into the kernel, like, the same way you talk to an operating system. All right, so basically they use the same idea as a pseudo terminal, device, and to talk to this VM application. Okay, so now the path become like this. If you need to talk to a particular device, right, you will trap into the host operating system. The host operating system will transfer control into the VM driver. The VM driver will invoke code over here that will allow you to talk to the actual device. All right, and same thing when the data comes back from the device, they also go through the same path. Okay, as we see that this can be done in the window manager, and the window manager perform fairly reasonably. Okay, so if they can do the same thing with the VM app over here, it will be just as efficient as a window manager.
The time is 20 o'clock.
All right, and this is VMware, how they solve the I/O virtualization problem, is to use the the original device driver and use the VM application, sitting in the same place as the window manager to transfer data between the VM driver and the actual device. All right. What about parallel virtualization, right? So parallel virtualization, if you can take things out of the operating system, what would you take out? All right, what about if you take out all the device drivers? Okay, so for people who want to run inside the data center, okay, they want to be as efficient as possible, they say, hey, go ahead, take all the device driver out. I don't really want anything to slow me down. Okay, so they will take out, all the pop-f code inside the kernel, okay, and also they will take out all the device driver, but now they have to replace with something. Okay, so basically they can take away with device drivers so they can have an efficient way to talk to the operating system. One of the companies that are successful in doing that is called Zen. Well, I guess Zen is open source, right? So it's really, it's coming from CMU. It's an architecture, okay? So the idea over here is that, here's your virtual machine, okay? And your virtual machine is required to take out all the I/O components, okay? And your I/O component will talk to another user level application. So this is, this is similar to the VM app sitting in user space, okay? And you do inter-process communication. So instead of doing I/O, reading from the disk, writing to the disk, you talk to a socket, and that so that you are talking some sort of a channel using shared memory, so you can communicate with another user process, again, like the window manager. And this is the guy that actually does all the I/O for you. Okay, so in that case, basically you change all your I/O and change them into communication code with another user process, so things will be a lot faster. When you communicate through the shared memory, you can write to shared memory without going through the operating system. Okay, so this is the one that actually knows how to talk to the real hardware. All right, so this way, this virtualized entity can be run a lot faster. And, Zen has actually become very popular in the data center now, because they have a major speed advantage over, the VMware approach, right? The major problem with the VMware approach is that it's going to be slow, okay, because, you're going to go into and out of, even though, technologies like window manager is fairly efficient, but it's still slower compared to, communicating directly with another application. All right, so here's a summary slide, right? Virtualization. There are two major kinds that we talk about. One is full virtualization, one is para-virtualization. In full virtualization, to virtualize CPU, VMware use dynamic binary rewrite, and for I/O, they have a split driver in VMM, and also they use the guest host operating system. So the host operating system already knows how to talk to all the devices. Okay, and I guess there's also they use a VM app. Okay, for communication, between the VM driver and the actual device driver. In parallel virtualization, the CPU, all the POP-F, instructions have been removed to be, hypervisor call, or you can think about it as an illegal instruction, anything that will trap into the VMM. Okay, and the I/O, there's no device driver. So these days, when you talk about virtualization, there's also a third kind of virtualization. I mean, it's really not a virtual machine, but sort of people call them virtual machine, and that's called, containers. Okay, so these are called containerized operating system, or OS containers. There's some open source project like OpenVZ that are supporting this. Okay. And this is not mentioned in the textbook, so I want to briefly mention it because sometimes people might confuse with different kinds of virtualization. In this particular approach, you can still run various virtual machines, but in this case, they all run on the same operating system. Okay, so the same operating system over here, they have a thin layer to interact with the application that are running inside this virtual machine containers. Okay, so basically this operating system over here, and again, what they're trying to do is provide isolation between different virtual machines. And one of the important things that they want to provide is that when you have virtual machine running in the cloud, one thing that you want to make sure is that if the virtual machine says, well, here is one piece of hardware. Sorry, the hardware is sitting down here. One piece of hardware that's shared by, let's say, 10 virtual machines. So when I buy this virtual machine on this hardware, I want to say I'm paying for 1/10 of the hardware. Okay, so therefore I want to verify that I'm getting exactly 1/10 of the hardware. Okay, I'm getting 1/10 of the memory, I'm getting 1/10 of the virtual memory system, I'm getting 1/10 of the disk, I'm getting 1/10 of everything. Okay, so how do you guarantee that? Okay, so if you use this particular approach inside the operating system, I can actually carefully manage so that I allocate resources separately for every virtual machines so that they don't really overlap. Then I can make this kind of guarantee that every virtual machine has exactly what they pay for. Okay, so the operating system over here it's going to make sure that, that there's isolation among all these data structures that are used inside these virtual machines. Okay? In the previous approaches, when you try to share the CPU, when you try to share the memory, it is possible that one virtual machine is going to end up hogging the processor. Okay? So people who are paying for those machines are going to get pretty upset. All right, so anyway, so this is just a sort of thin layer, and the operating system is trying to make sure that everything is containerized so they don't, interfere with other virtual machines. All right? Okay, a little bit about virtualizing virtual memory. What does that mean, right? Okay, so if you have a user process, the user process has an address space, right? So the user process thinks that's the virtual machine that they're using, okay? But in reality, we know that it's the operating system that are controlling, real memory. But if you're running on virtual machine, is the operating system controlling real memory? Okay, no, right? Because the memory map that is set up, well, they're fake. Okay, the memory map they're set up are supposed to be set up inside the virtual machine. So they're really not the actual memory map. All right, so so I sort of mentioned, right, inside the guest operating system, if you manipulate with the CR3 register, well, you're going to trap into the virtual machine monitor, and the virtual machine monitor will emulate that particular instruction, make you think that you have set the CR3 register to point to the right page table. Okay, but what the guest operating system think where the page table is really not the real page table. Okay, only the VMM knows where the real table is. Okay, so in that case, the VMM is actually in charge of the real memory. Okay, and this is the guest operating system, right? The guest operating system thinks that's what it's dealing with, and the user program thinks that they're dealing with, an address space abstraction, which of course we know now it's completely fake. Okay, so in that case, if we look at the memory map, okay, in the guest operating system, it thinks that it has a page table. Okay, this page table maps virtual page number to physical page number, but again, that's not the real page table. Okay, the real page table is built by the VMM inside over here, and VMM over here is actually is the one that has a real page table. Okay, so this example is showing only 4 entries inside the page table that the virtual machine thinks that it has. All right, so in this case, entry 1 and 2, they're invalid. Over here, I stands for invalid. Okay, entry 0 point to page 1 of the physical memory. Okay, but again, this is fake physical memory. So where is page 1 really point to? So over here, VMM says for this for this virtual machine, page 1 actually point to page 3 in the actual physical, the physical memory. All right, so basically you have to go through 2 levels of interaction, right? If you try to access, if the user program try to access this particular, access entry 0 over here, you get to translate into physical page 0, but that's virtual physical memory. So it needs to go through 1 level of translation again, go to entry number 1 here to find entry 3 in the physical memory, and this is where the real physical memory is. All right, so if you look at this page table, right, this page table, 0 mapped to 1, 1 and 2, they're invalid, 3 mapped to 2, and inside the virtual, inside the virtual machine monitor, the virtual machine monitor will map page 1 to physical page 3, and then virtual page 2 to map to physical page 1. Then if you combine the 2 page table, this one and this one together, you're going to get this particular table that says page 0 mapped to physical page 3, okay, and page 3 mapped to page 2 mapped to page 1. This guy actually mapped to 1. Okay, and page 1 and 2, they're invalid, so they can be left as is. Okay, so this page table needs to be constructed inside the virtual machine monitor, and then when you try to set the CR3 register, what do you set the CR3 register to? You set the CR3 register to point to this memory location. All right, so inside the guest operating system tried to set the CR3 register to point to this page table, the page table sitting at that memory location, okay? But when it's trapped in the operating system, when you emulate that, you're going to end up CR3 register need to point to this page table. Okay, so this page table is called, I guess, unfortunately, they reuse the same term as shadow. This is called the shadow page table. It has nothing to do with shadow objects. Okay, so this page table is the combined table from this one and this one. If you combine them, you're going to get this one, and the CR3 register needs to point to this memory location. All right, so things get a little complicated. So how do you really support, so every time when you modify any page table entry, okay, if you modify, where this guy points to, right, physical page number inside handle page file, in Unix, right, you're going to call pt map to say where does it map to. Well, that's going to be a sensitive operation. So you're going to trap in the virtual machine monitor so they can fix up the shadow page table and have the right entry to be pointed in there. Okay, so you want to get so when the guest operating system modifies this entry, you want to trap into the virtual machine monitor so you can fix this entry with the corresponding physical page number. All right. So how do you do this efficiently? Okay, so one way to do this, so again, if you are allowed to change any code, okay, you will change all your, PT map code so that if you run inside a virtual machine, you can do the, do the translation directly. Okay, how do you do the translation directly in your guest operating system? You make a hypervisor call. Okay, so basically what you can do is that you can make a hypervisor call so that you can combine these two page table inside, inside the virtual machine monitor when you emulate that instruction, so you can build this table. Okay, so this is a sort of a faster way, so you don't have to look around inside the kernel to look for stuff. You can just directly make a hypervisor call to provide the correct table. You can also, the second approach, fixing the hardware. Again, most likely when you run dmesg and look at the boot messages on your machine, you're going to see that all your laptop supports something called the EPT. I think it's either in lowercase or uppercase. You look for it. It's called extended page table. Okay, so in that case, when you're running inside the virtual machine or a hardware that supports EPT, then when you perform the operation, the hardware will actually traverse both tables. Okay, so in that case, what you need to do is that when you do the virtual address translation, okay, the hardware is actually smart enough that it knows that you're running inside the virtual machine, so therefore you need to traverse both this table and this table, because this one will traverse, when you return, you're going to return into, in this case, the physical page number 1, but this physical page number 1 is inside the virtual machine. So therefore, you will go, you need to find out where this particular location is. And again, hardware will know where this is. And this one will do the translation from 1 to 3, and that will map you into the physical page number. Okay? And I think the textbook provides this, pretty complicated picture because for the Intel, they're doing multi-level page mapping. So, whenever you go through one level of translation, you have to go through, another level because you're running inside the virtual machine. Okay, so this is where the guest operating system is doing the code running inside the user program of the guest operating system when they do the virtual address translation. Now it will go to the lower level and do another level of translation. Okay, because right now every code, unless you're executing inside the virtual machine, any code inside the user space has to go over 2 levels of translation. All right, so this can be done, inside hardware. So if you look at this, right? It's 4 levels of translation. Okay, so it's going to become really, really slow, and it's very, very important your translation look-aside buffer has really good performance. Otherwise, every memory lookup is going to take you, quite a while. All right, the last part is talking about another approach to shrink the code in the kernel, and this approach is basically taking all the code outside of the kernel. Okay, so what can you take outside of the kernel? Can you take the file system outside of the kernel? Well, you can try, right? So this approach, take the file system outside the kernel. You take the line discipline outside the kernel, you take networking outside the kernel, you try to take as much stuff outside the kernel as possible. But in this case, you still need to provide, so what goes into the kernel? Okay, process management, okay, threads and processes, should they be in the kernel? it will be very difficult to take that outside the kernel. Okay, memory management. Okay, can you take out of the kernel? Page table and all that kind of stuff. It's going to be very difficult to take out of the device driver. So you can also take device driver outside the kernel. Okay, but again, it turns out that performance usually is poor when you take devices. Your I/O performance is going to be poor. So every time you do I/O, your operating system is going to look sluggish. Okay, so maybe the device driver, even though people, for many years, people keep trying to take the device driver and put them in user space. Okay, one thing that you need to add inside the kernel over here is something called message passing. All right, because basically you need a way for you to communicate between this application and things like file system. Okay, if you move the file system into user space, how do you open a file? Okay, so this guy, when they try to open a file, should it call open? I mean, open, the file system is inside the user space, right? Okay, so it doesn't even seem appropriate that it should call open because now this becomes a user process that's running. So you need some way to communicate with these applications sitting in user space. Okay, and the way that you're going to use to communicate with these user processes are basically called message ports, okay, or MSG ports. All right, so we need this new primitive. So the idea over here is that whenever we create a file system right here, we're going to create a message port, okay, message port inside the kernel. So when you try to open a particular file, you communicate with this message port, and you're going to end up sending a message to the file system. Okay, the file system will handle managing of that particular file. Okay, so clearly this is sort of a if the performance is good, this is really nice because now you can write all your file system code inside the user space. And if you have a file system crash, who cares? You didn't crash the kernel. Okay? If you have, networking code that's going to crash, again, it's perfectly okay. All right? So this is a good way so that your operating system gain reliability, but what you lose is losing performance because now if you need to talk to the operating system, talk to the file system, you need to go into the kernel, come back into user space, and the file system will talk to the device, it will go into the kernel, and when the response needs to be returned, again, it has to return from this path. Okay? So every operation is going to be at least 3 times as slow. So by the way, this is a problem, okay? Shrinking the operating system is an old problem. So one of the reasons people want to work on the microkernel is it's kind of cool because if people ask you, what are you working on? I'm working on microkernel. Wow, it's really cool. Because it's a really, really difficult problem. For years, people have tried to do this, and they haven't been successful. Okay? All right, so lots of advantage for having a microkernel. Okay? But the main problem is that it's really, really slow. Okay, so CMU started a mock project, I guess in the late 60s and the 70s. So, they tried this very, very long time ago. They started in CMU. Later on, they got maintained in Utah. And went into some of the companies started adopted. One of the companies called Next. And for those people who knows, Next was where Steve Jobs went. I guess after he got fired by Apple for the first time, he went to Pixar, went to Next, and eventually when he come back from Next back into the CEO of Apple, he brought back 2 things from Next, right? One is the graphical user interface that's using Next, and unfortunately, it was programmed in Objective-C, and that's why these days, when you want to program the Mac, you have to know Objective-C, okay, because it took that from Next. And the other thing he took from Next is Unix, okay? So the Unix that he took back from Next, this one actually started out with mock, playing around with microkernel, but in the end, everything goes back into the monolithic kernel, because if you run everything in the user space, you just cannot compete with company, like Microsoft or Sun Microsystem. Okay, so in the end, if you want a reasonably perform, system, then everything went back into the monolithic kernel. All right, there's another version of microkernel running. GNU has a herd project. It's really not clear who's using this particular system. And the reason, again, it's poor performance. All right, so I guess I drew part of this picture already, right? When you have a file system, you have a message port, and then you make an operating system call to create this message port, and all the message port live inside the kernel. And the user processes, they will use these message port to communicate with all these entities. Okay? So if you want to open a file, you want to rewrite to a file, you send a message to the message port, the message gets forwarded to the file system, and if the file system needs to talk to the device driver, it has to use the message port for the device driver in order to communicate with it. Okay, and then how does the device driver send data back to the file system? Well, you use the same kind of mechanism. In order for you to talk to the talk to the file system, you need a message port for the file system. Okay, so in this case, what happened is that, okay, the response port is created for the file system, okay, and the device driver will send the response through this port, and it will go back to the file system. And for the user application, when it needs to, when it talks to the file system, it says, when you're done, send the response into this response port. So when the file system is done, it sends the response back into the message port, and that's how the application pick up data from the response port. All right, so you can already see the performance problem, for talking this way, right? You go up and down the operating system, the user space and the kernel space several times, in order to achieve communication. All right, I have a couple of slides more to finish about message port, and then we'll finish that at the beginning of the next lecture, and we'll talk about scheduling. All right?
That concludes CS 402 on Monday, July 28, 2014.